Yo, what's up guys? So today we're going to be modeling functions again, okay? And so, if you like this content, consider subscribing, but let's get into the video. So, there's a short section of this module or chapter that talks about appropriate labels and ranges of graphs. But, I think it's pretty simple and, I think we've all done it before. And so basically, if you have our two axes, so we could have this x-axis or y-axis and x-axis. The x-axis is equal to whatever x is measuring, or the dependent variable, right? So if, I could just have p is equal to, 20m, and the x-axis would be whatever m is modeling, so whatever the independent variable is modeling. And same thing with the y-axis. We could just write this like that. The y-axis is whatever the dependent variable is. So whatever this p is equal. It doesn't have to be p. It can be whatever variable, just whatever the dependent variable is. And if it asks for a certain range or a certain x or y value that it stops at, or you need to see or find while graphing, you can just manipulate the size of your graph to make it fit the ranges. So give a bigger view of it or a smaller view of it. Okay, so next I'll briefly talk about setting up equations with word problems. So this lesson kind of covered setting up rational equations, inequalities, and exponential equations based off of word problems. I don't really have any examples right now, so I would suggest checking out Khan Academy Chapter 12, Lesson 4, and it's all about solving equations, setting up equations based on word problems. And some pointers I would give is watch the wording. So especially if it's an inequality problem, you're going to have to decide if it's one of these, like a greater than or less than, or a greater than or equal to, or less than or equal to. So just watch the wording, make sure, and it might not be an inequality problem. It might be asking for an equation. And normally you would model interest problems with exponential equations. I think these pointers may be important, but I think that watching some examples and practicing it on your own is the best way you can learn this kind of stuff. And now for the main part of this chapter, modeling with multiple variables. So let's say we're at a grocery store and you have flour, milk, and eggs. And so this column is for dollars per pound. So for flour, it's $8 per pound. And our guy, how about, Mark, bought B pounds of flour, and milk, same thing, C dollars per pound, he bought D pounds. Eggs, E dollars per pound, and he bought F pounds. And so all of this ended up, it cost, how about $20, okay? So how can we make an equation to model this? Well, we know it's going to be equal to $20, right? And so if it is dollars per pound, let's just start with flour. If it's $8 per pound and he bought B pounds, then you just multiply A by B. So we're going to have AB. So $20 is equal to AB, but that's not the only thing he bought, right? He also bought milk and eggs. So we're going to do plus, so AB plus, same thing over here, C times D plus E times F. And that's how you would model these problems. So, I used all variables here except for the $20, but obviously you could substitute. So maybe you could say he bought, 2 pounds of flour, right? So then that'd just be 2A, or, you could say, I don't know how much it costs per pound of eggs, but maybe it's, $10 per pound of eggs, so 10F, right? And maybe it's, I don't know how many he bought, maybe 1 pound of milk, so 1C, or just C. And so, obviously I just deal with variables, but of course it can occur with values as well. And now we're going to be talking about speed, okay? And just to write up here, we can do our speed formula. So speed is equal to distance divided by time. And this is going to be important with our problem. Okay. So we got two guys. We got Bob and we got Bill, okay? So they are walking to school, okay? So Bob is X miles from school, so X miles from school, while Bill is Y miles from school, okay? And so Bob walks z miles per hour, while Bill walks 4 miles per hour. So we're going to set up an equation to model this scenario, assuming that they left at the same time and arrived at the same time. So they took the total same amount of time. Okay. So how can we solve this equation? Well, if we know that their times are equal to each other, if we know that their time is equal to time, then we can just say, okay, well, what is time equal to? This is where rearranging our equation could come in handy. So multiply by t multiplied by t. So we get ts is equal to d divide by s, and if we bring that up here, we find that t is equal to distance divided by speed. Okay? Distance divided by speed. So if we know that their times are equal to each other, then we know that their distance divided by speed of Bob is equal to distance divided by speed of Bill. And so with this, we can just plug in our distance and our speed. So we know that Bob is x miles and moved at z here. That kind of looks like a 2. I have to cross my z's. And went z miles per hour, averaged z miles per hour. And we know that Bill is y miles from school and averaged 4 miles per hour. So this is an equation that we can set up to model this scenario here with Bob and Bill walking to school. So now on the topic of multiple variables, we will be talking about how changing one variable in equation can change the whole thing. Okay? So let's say that we have 10 is equal to a minus b divided by, how about x divided by y. So let's talk about how changing this equation or this expression can change the outcome. Okay, so let's see how changing one variable in this expression can change this. Okay, change the 10. Okay, well, let's say x is 2 times larger, so this is going to be 2x. Okay, well, let's rewrite the expression. So a minus b divided by 2x over y. And so we can rewrite this, right? So a minus b divided by a fraction, right? And when you divide by a fraction, you can just multiply by the reciprocal. So a minus b divided by 1 times y over 2x. And so that gives us y times a minus b divided by 2x. And so compare this to the normal equation, right? So a minus b divided by x divided by y. We can rewrite this. So a minus b over 1 times y over x. And so we get here y times a minus b divided by x. And so the numerators are the same, but the denominator of this one is twice as big. So we can say that it's going to be half as much. So when we multiply x by 2, so when it's 2x, it is equal to 5. So 5 is equal to a minus b divided by 2x divided by y. So let's try to change another variable. How about we make y 3 times as much, okay? So we could say what is equal to a minus b divided by x divided by 3y. And so let's set up our equation, right? So a minus b divided by 1 times, remember, when you divide by a fraction, you multiply by the reciprocal. So 3y divided by x. So, sorry, that was bad x. Boom, big X. So 3y times a minus b divided by x. And let's compare this to our normal equation, which would be, or base equation, which would be a divided by b, or sorry, a minus b divided by 1 times y divided by x. So we get, let me just move that over here. So then that would simplify to y times a minus b divided by x. And notice, this is just y, this is 3y. so it's going to be 3 times as much. So we know that a minus b divided by x divided by 3y is equal to 30. Hey guys, thanks for watching. So this is my last Algebra 2 video, so you're done. That was all Algebra 2. So I don't really know what I'm going to do next. Probably not calculus yet because I'm not there. But I might do some more or less complicated stuff. So I might go back to Algebra 1 or geometry, which, I really liked Algebra 1, so I might do a series on that. I think that'd be cool. But yeah, but that's kind of it for now. So yeah, thanks for watching, and maybe I'll see you guys in another video. So, peace.